Hello folks, so in this video I want to talk about what you can do in order to graph a function when it's not factorable. Well, this is kind of actually like a teaser video more than anything, but I'll explain why. So let's take a look at this function, y equals x squared plus 4x plus 1, and I want to find the x-intercepts. So based on what we have been doing, the way I would do that is I would try to factor it and use the zero product property. So I'll set y equal to 0, we get x squared plus 4x plus 1. If I can get it into its factored form, then I can use my zero product property and it's easy peasy from there. So let's try to do that. Okay, so I'll start off with my generic rectangle. X squared in one corner, 1 in the opposite corner. The two numbers I'm looking for, I need to multiply them and get them to 1x squared, because that's one diagonal. And we know that both diagonals must be equal. And when I add them, well, they have to give me my x terms, which add up to 4x when I collect them. So it needs to add up to 4x. I think you can already see the problem here, and that, as far as I can tell, there are no integers that are going to make this work. I could have maybe, 1x and 1x to multiply to 1x squared, but those won't add up to 4x. If I have negative 1x and negative 1x, that will multiply out to 1x squared, but unfortunately won't add up to negative 4x either. So as far as I can tell, this is unfactorable. The question you might ask yourself is well, what does that actually tell me about the graph? What can I tell about this graph? So I can tell that it's got a positive x squared term, so it must be open up like a cup, like that. And I know that its x-intercept is at 1, so maybe this graph looks something like this, where there is no x-intercept. But I think we can see it's entirely possible that this graph might look something like this, which does have x-intercepts, and so we really don't know. This could be, no x-intercepts. Heck, it could maybe have exactly 1, or it could have 2. So unfactorable on its own is not enough to say that there are no x-intercepts. So I do think that that is a reasonable assumption. We've been factoring it in order to find the x-intercepts for a long time now. And if that can't be done, then surely there must be no x-intercepts. But that's not actually the case. So there are no x-intercepts. Okay, so I'm going to pull up my my Desmos here and show you what this graph actually looks like. Alrighty, so we're back in Desmos here, and we can see, again, my function x squared plus 4x plus 1 actually does have x-intercepts. And so, as expected, it's got a y-intercept of positive 1, and it actually does go below the x-axis here, and it opens up. So if it goes below the x-axis and opens up, of course it's going to have x-intercepts. But where are the x-intercepts? It turns out that they are at these weird, funky numbers, and these actually end up being irrational numbers. So it says negative 3.732, but this actually does go on and on and on forever and doesn't repeat. It just rounds it off. And likewise over here, it says negative 0.268 and stops, but in actuality, it does go on forever. Okay, so here's the question is, well, how did the computer get this? Or how could we get this? So I'm going to turn back over and I'm going to give you an alternate form of this equation. Okie dokie. So here is the same equation, just written in a different way. And and then you're gonna, if you're really hungry to learn more, you're gonna really ask, well, how the heck did you get from the standard form to whatever this form is? And I'm just gonna ask you to hold on to that question for now. Okay, I just want to show you what this form lets us do in this video. Okay, so if you don't believe me, which you shouldn't believe me, multiply it out and see if you get to the same standard form equation. So I will do that just real quick, just to prove that it works. If I multiply out x plus 2 squared, again, that's x plus 2 times x plus 2. So I'll end up with x squared plus 2x plus 2x, and then plus 4, and then minus 3. So we can see here, these are going to give me x squared plus 4x. 4 minus 3 is going to give me plus 1. So I did not lie to you. This does actually work. So these two equations are exactly the same, and then just written differently. Okay, so how does that help us? Well, check this out. I could find the y, or sorry, I could find the x-intercepts. Again, the process is going to start off exactly the same as it always does by setting y equal to 0. So I'm going to set y equal to 0. And my equation now, instead of saying y equals this times this, it ends up being x plus 2 squared minus 3. So I can't use zero product property anymore because I don't have an exact, product on the right side. There's a product, sure, x plus 2 times x plus 2, but then there's that minus 3, so it doesn't quite work out. Now, one thing you might want to do is, okay, well, I'll multiply it out, get it into standard form, and then factor it. That would be great if it was factorable, but we already showed you, or we already talked about how this thing isn't factorable. So try not to do that. But what we can do is just solve it like any other equation that we had been solving before. And the way to do that would be to, well, add 3 to both sides. Once I do that, well, I'll get 3 equals x plus 2 squared. Oops. Let's clean that up a little bit. X plus 2 squared. And just like before, well, if I want to clear up something squared, I need to take the square root of both sides. And so yeah, you're gonna end up taking the square root of 3, which is not a pretty number, but hey, it happens. This could have happened when we're talking about linear functions as well, where your slope might be the square root of 7. And so it's a weird number, but hey, it's a number. And so when we take the square root of 3, when we take the square root of both sides, we'll end up with the square root of 3, excuse me, is equal to x plus 2. And we can solve this by just subtracting 2 from both sides. And it is going to seem really weird, but your final answer over here just means, oops, I'm going to write it like this, negative 2 plus the square root of 3. Okay, this could also be said as the square root of 3 minus 2, but I'm just going to leave it like this just to be really, really clear. So this is one x-intercept, and if I throw it into my calculator, this is approximately equal to, let's see, that ends up being negative 3.732, which, again, approximately, was one of our x-intercepts that we saw in the graph. Okay, but hang on. If we go back to Desmos, I'll pull it up right here, we actually can see that there was a second one, and it was over here. But my equation only had one solution. So what gives? Well, it comes back to this step right here. Oops, sorry, this step right here, the square root step. Let me step aside over here, please. If I told you that x squared is equal to 25, what would you tell me? Well, of course, you would tell me 5. But there's often one that gets easily forgotten, and you feel kind of bad for it because they get so forgotten. It's never fun to be left out. But there's a second solution, remember, and that's negative 5. And the reason I think this gets so easily forgotten is that when you take the square root of both sides, and if you were doing this with your calculator, the square root of 25, according to the calculator, it only gives you 5. Because it assumes you're only asking for the positive square root. We call it the principal square root. But remember, there are two numbers that when you square it, get you to 25. It's 5 and negative 5. And so just like over here, just like that, over here we're going to have two answers as well. So, well, what number squared gets you to 3? Sorry, gets you to 3. One answer is the positive square root of 3, which is this one that we got. But you could also take the negative square root of 3. Again, the square root of 3 is around 1.7 something. So negative 1.7 something would also work. Again, how could I confirm? Well, I'll square both sides. If I square both sides, this side, I'll get up to here. If you take the square root of negative 3 and square it, well, again, negative times negative is a positive. Square root of 3 times the square root of 3, by definition, is 3. Right? So whenever you take the square, if you're looking for the solution to something squared equals a positive number, you'll end up with two answers. A positive version of the number and a negative version. So let's clean this up. So you should actually end up with two solutions. One there with the positive square root of 3, and then negative square root of 3, x plus 2. But again, this process ends up being the same. This is probably reminiscent of a absolute value equation at this point, where you get multiple solutions. And your other x value is x equals negative 2 minus the square root of 3. And this is why I wrote it like this. As you can see, in both of these cases, your x-intercepts have that negative 2, and the only thing that's different about them is negative 2 plus the square root of 3 or negative 2 minus the square root of 3. And this is actually always going to happen once you solve an equation set up like this. Okay, we'll talk more about that in the future though. And again, this value, if you throw it into the calculator, is approximately 0. Let me double check here. It should end up being this negative negative 0.268. Okay. I do want to show you one more thing though, which is kind of the purpose of this whole thing. Okay, so those are the two x-intercepts, and again, we could double check if you don't believe me. Negative 2 plus the square root of 3 ends up being negative 2.68 if we round it. Negative 2 minus the square root of 3 ends up being, wait, what happened? Oh, sorry, I had these backwards. My bad. Okay, so this first one ends up being over here, and this one, oopsies, ends up going over here. Sorry about that. I didn't actually calculate it. I just assumed it was one of them. So my bad. Okay. Here's the other thing I want us to notice. This is the same equation again in red and blue. But what else do we notice? Well, actually, if you take a look right here, you can see that the vertex is actually built into the equation. And that's why this form of the equation is called vertex form. And so let's see, the equation y equals x plus 2 squared minus 3 has a vertex at negative 2, negative 3. And this is kind of awkward where you see, okay, so it's the opposite, the x coordinate has an opposite sign of what it does in the equation, but the y value has the same sign, and that confuses a lot of people. And so this might help is if we instead wrote it like this, where y, I'll just move the 3 to the left side, plus 3 is equal to x plus 2 squared. And now you can see, okay, you just flip both signs, and that tends to help some people. Okay, so in general, the vertex form of a quadratic function looks like this. I'm going to say y minus k is equal to a, because sometimes you'll have some coefficient right here. In this example, a was equal to just 1. And we'll have x minus h squared. The neat thing about this is that, again, the vertex is built into the equation, so the vertex happens at h comma k. So again, this says, this one can be written as y minus negative 3 times 1, x minus negative 2. And so that's why the vertex is at negative 2, negative 3. Okay? And also, A tells you the orientation of the parabola. So check this out. If I changed from 1 to negative 1, or let's make it negative 2, notice that it goes downward now. Okay? So A tells us the orientation, just like it always does. Okay? So hopefully that helped about how you can find the x-intercept if it's not factorable. If the function is not factorable, you're going to want it instead in vertex form, and then you can solve the equation like any other equation. Okay? Now again, the hard part is how do you turn the function from standard form into vertex form, and that's going to come in a later video. I'm going to keep you in suspense for now. Okay? What you should do right now is just, make up a random function, right? So just make up a random vertex form function and get used to graphing it. Find its vertex, find its x-intercepts, And this whole like backward signage, you'll get used to it as you keep practicing it. Okay. In the next video, I want to talk about why or what the different uses of the different the different forms of the quadratic function are useful for. Alrighty, so stay tuned for that video, and thanks for watching. I know this one was kind of long, but hopefully it was helpful, and I'll see you around.